All right, we finished everything about the basic setup of trigonometries. In chapter 5, we did it in right triangle. Okay, and then in chapter 6, we did it in terms of unit circle. So now we are very familiar with how to transform from, numbers and angles to trigonometry values. The next job is something called analytic trigonometry. So basically what we're trying to do every time we have something called analytic is we're trying to shift from the realm of geometry into algebra. And this is actually not something new because we have done this a lot of times before. For example, before you have straight lines, you can draw triangles, you can draw lines, do all kinds of things in geometry. That's one thing. But then, instead of doing this, what we can do is we can change them into y equals ax plus b by change a line to y equals ax plus b by putting them into a coordinate system. The advantage of doing this is, number one, you standardize everything. Okay, you have another way to represent the same thing. And number two, you can use all the tools you have in algebra, such as simplifications, identities, to actually do some tasks which are super difficult to do in geometry. For example, if you know the line, two lines, can you find where the intersection is? If you just draw by geometry, you will need to prove, the sides, relationships, similar triangles, that's what you're going to use. But in analytic geometry, all you need to do is just, I have y equals ax plus b for one line. I have y equals cx plus d for another line, if I could put them into coordinates. And then I put them together, I solve it using solving the equation. Solving the equation is not something you can use in geometry, but that's certainly something you can use in algebra. So you have a whole new set of toolbox you can use as long as you can transform the geometric problem into algebraic problems. Okay. Moreover, the geometry is really easy to understand and visualize. To give you an idea of what's going on, when you transform into algebra, you lose that. You just see two equations. You have no idea what they represent before, unless you do an additional step to think about them in lines. But you lose understanding, you lose visualization, but you do obtain precision. Because solving equation can be super, super accurate. You can solve for something which is like, square root of 3 with 1/2, compared to if you do things in geometry. Probably our mind can only do something with integers. At most, some simple fractions, like 1/2 the size. That's the beauty of this. So now what we want to do is we want to take everything in geometry of trigonometries, and we want to do the analytical side. That means from now on, we will not do things at the right triangle level. We will not do things at the unit circle level. We will do things at algebra level. But the good news is, every time you got stuck with algebra, you always use this one to help to visualize or think about this, but you don't use it to solve things. Okay? Now, the first thing we want to do is trigonometric identities. The first thing we want to write down is all the trigonometric identities we know so far. Moreover, they are simple, so I'm going to put simple trigonometric identities. Including several sets. The first one is going to be the reciprocal. We are very familiar with this now. We have 3. There are sine and cosecant. They are cosine and secant. And finally, they are tangent and cotangent. That's the first 3 sets of reciprocal. The second one is, of course, the Pythagorean. We again have 3. They are sine square plus cosine square, which is probably the most important one. Okay, and the tangent square and the secant square, that's probably the second popular one. The third one we rarely see but I'm just going to put it here. And usually, if you don't even know about this one and this one, you can get both of them from the first one by doing additional work. So I would say this one is the most important, but in our class, make sure that you know this too. Number 3, odd and even identity. We talked about this before. We say, hey, out of all the 6 trigonometric values, functions, secant and cosine are even, the rest are odd. With that in mind, that simply tells us, if you put a negative here, sine, tangent, and therefore the reciprocals, cosecant, cosecant t. Cotangent. And they are all the odd functions which satisfies this identity. And we have all the even ones, which are cosine. If you put a negative, it's equal to not putting anything. Therefore, secant, which is 1 over cosine. These are called the even ones. So if you forget about what's going on, a simple thing you can do is just draw the unit circle. Okay, and then put a t here, and put a negative t here. This will be the sine. You can see they are the same size, but the one is positive, one is negative, and this one here will be the cosine. For both negative t and the t, because they share the same cosine. According to the definition of cosine, which is the x value of your point. These 2 points, even though they have different y value, they have the same x value. Okay, so you can actually easily get the information from this unit circle if you forget. I personally memorize this compared to what we have here. Finally, we have the last set, which are the co-function identity, which we didn't address much before. But if you think about it, it's very easy to understand. This is the first one. Okay. So what do you have here? You have the transformation from sine to cosine, which is the co-function. Okay. From tangent to cotangent, from secant to cosecant, of course. Why is this true? If you think about it, we can do it in a brief way about how to do it in right triangles. In general, you can do it, but for right triangles, I think it's pretty easy to do. What this one tells you is, remember, pi over 2 is 90 degrees. That means if this is x, this one is going to be the pi over 2 over x. So pi over 2 minus x and x are complementary angles, which means they are basically in the same right triangle, except one is on the left, one is on the right, or one is on the bottom, one is on the top. They form the same right triangle. Therefore, your opposite is actually my adjacent. Okay, and your adjacent is my opposite. And now if you remember the definition between sine and cosine, you can easily verify. If you sum together equal to, you are this angle here, and you are this angle here, your sine is actually my cosine. Okay, and your cosine is my sine. So that's a way to transform from the sine, tangent, and the secant to the corresponding co-function. So let me write it down. And the secant to pi over 2 minus x equals cosecant pi over 2 minus x. And vice versa. That also means cosine, if you do the same thing, you just receive sine. And so on. Okay, so that's what we call co-function, going from sine to cosine, tangent to cotangent, and secant to cosecant by doing a pi over 2 or 90 degree minus x to get the other angle in the same right triangle. Now with that, we can do a lot of interesting things. Number 1, remember the graph, and we say, hey, this one has a graph which look like this. Now we have this graph which look exactly similar. Now, if you think about it, it's very easy to understand why. Number one, cosine is the same as sine if you do this. All right. Now, that is going to be what? That is going to be sine x minus pi over 2 if you put a negative sign here, but because it's odd, you put it here. So what is it? This means sine x shift to the left, to the right by pi over 2, and then flip over, or with respect to, the x-axis because of this negative here. So what you need to do is, you need to take this one, shift to the right by pi over 2, okay, flip. You got this. Okay, now continue. Of course, your cosine looks like that way. Okay, so with the identities, actually, it has some hidden geometric relationships there. But for now, we can forget about all this. We just remember this simple formula. You see a pi over 2 minus x, go to the corresponding cofunction. That's it. All right. With all these identities, now what can we do? We can do two things. The first one is we can see a trigonometric expression and simplify it. This is nothing surprising. It's almost like, okay, when you see something like that, can you simplify it? Well, we know an identity, that is. Okay, then we can change this one to be this. From here you can see, this is something we did before for simplifying expressions. The idea is we know some standard simple identities. We only have a handful of them. But then, next time we see something complicated, it has many parts. You go to each individual small part and try to change it into some other expressions using the basic identity. And eventually things cancel out. Okay, and finally you can have something that is simpler. Now we want to do exactly the same thing. This time it's just for trigonometry. So the idea is the same. Go to every single part of the expressions and try to see can you change it using some basic trig identities to some other expressions, and hopefully the new expression can simplify each other. And there is nothing better than going over some examples. So cosine x So what do you do? Well, number one, it's not easy. So you need to do all you can do. And maybe the first time when you try something, you cannot get it done. And that's okay. So for me, I look at this one. I say, well, what do I recognize that I may be able to change them into something else? Cosine is easy. Sine x is easy. There's no way I can change them. But the tangent, if I want, I can change it to be sine over cosine. Does it help me? Probably, because now I have three types of trigonometries. I have sine, cosine, and tangent. But if I change the tangent to be sine and cosine, at least I only have two trigonometries. Hopefully after that, they cancel each other. So the first thing is change this to this. It may not work, by the way. We just give it a try. I do know this. Okay, at least they look different. Now can I simplify more? Well, I know I can merge these two to be sine square x on the top. Okay. And if I want to simplify further, this is something you have done before. Some integer plus some fraction, maybe it's not a bad idea to have the common denominator so you can at least combine them. Will things become better? I don't know, but let's give it a try. Okay. Do you recognize more? This is 1, which is an identity. So this is 1 over cosine. Okay. Now, do you know what that is? Well, I have a better way of writing that, even though they're the same. It's secant. Therefore, after you simplify everything, this long expression can be simplified into a single term. That means a lot of terms, even though you write them there, they're redundant. They cancel each other, which is not necessary. Which is the same as what we had before. So what did you do? Number 1, you recognize some trig identities here and here. You recognize them, so you change them to something else. Tangent, don't do it, do sine over cosine. Sine squared plus cosine squared, don't do it, change it to 1. And of course, changing it to 1 is better. And then finally, when you have 1 over cosine, you change it to be secant. So there are 2 major things you need to know. The first one is you need to know the trig identities. Let's call it the simple identities. You need to be really fast and familiar with them. That's why in general I recommend memorize them. You can put them on a formula sheet. Okay, you can look for the formula sheet every single time. But just imagine if you don't have those kind of things in your mind, every time you may have 20 things to check. It's possible it's from the left to the right. It's also possible it's from the right to the left, or even some variations like this. Maybe you are not even able to recognize until you do some additional work in your mind and realize, oh, actually that's the same identity here. But on the formula sheet, you will only have this. You will not have this. So my recommendation is actually memorize all of them, so they constantly just boil in your mind, and finally you become super quick. You can reflect them because it's in your mind, not on paper. Searching something in the library of your mind is so much quicker and more accurate than searching it on a table or on a formula sheet. So don't use formula sheet. That's the reason I don't allow a formula sheet here. You can use it the first time you learn it or to remind yourself, but don't rely on it. The second thing is simple algebra. There are some things we did during the process. That is, we did the common denominator from here to here. And that is just simple algebra. So what you have is some common sense from before. When you see 2 fractions, get the common denominator. When you see both sides, you can cross multiply. Okay, things like that. So nothing new, except for you need to know a lot of simple identities. Now let's try another one. All right, now what do we have? And you probably know now you have sine, cosine, tangent. The first job is probably doing this. Again, there's no guarantee this will help you, so try several possible ways. Second, probably if it were me, I would just do the common denominator. From the first term, from the second term. Like we said, boil everything out because you're looking for trig identities. And that's why I say if it's in your mind, you are actually consciously looking for, if I see a cosine square, I desperately wish I have a sine square somewhere, and in this case you have it. This is one. Can you do more? Well, you have sine x on the top, plus a 1. You have a 1 plus sine x on the bottom. Once you simplify everything so they cancel out. You have a 1 left on the top, you have a cosine on the bottom. This one again is secant x. Beautiful. So the first one simplifies to secant x. The second one, after simplification, becomes secant x. And before you do that, there's no way you can recognize right away they are the same thing. But actually, after simplification, they are the same thing. All right. We can do more, but I think we can stop here. You got the idea. The rest will just be trying more examples by yourself. Some of you are maybe very quick with this. It's very easy if you have a very strong algebra background. Now you just need to memorize additional trigonometric identities. If you're kind of a little bit slow at the beginning for this, take your time. Just do more practice. And keep in mind, the key point is you need to memorize this. Do not use a formula sheet. So if you did a lot of practice and still wondering why am I not improving, you need to ask yourself, did I use a formula sheet? If no, throw them away. All right. Maybe you start to wonder, where am I going to get those kind of complicated trig relationships? Like something, why do I care about something look like, you know, cosine x plus tangent x, sine x, and maybe divided by secant x? Why am I going to get something so weird? The reason is because in real life, you know, trigonometry is for what? It's for right triangles, right? So very luckily, you only have one right triangle to think about, and the trigonometries are super easy. But in real life, it's very possible you have some complicated trigonometries. I mean, this is not even a complicated shape. Maybe you're trying to build some kind of grid to support a certain kind of structures in real life. Okay, maybe you have x here, maybe you have a y here, maybe you have a theta here, things like that. So from here you can see, if you're trying to say the relationship between maybe the force, maybe the material length, here and here, to set a relationship between them, let's say this one is half the size of that, in order to make this shape to work, you have to use the multiple trigonometries to first find the relationship between here and here using the trigonometry of this. And maybe find the relation between this and this using the trigonometry of this angle, and maybe this and that to find this, and then just keep going. So once you realize the relationship from here to here, you probably use some trigonometries in between. You maybe use a lot of trigonometries in between. And of course, and there's a hope, that is, maybe some of them will cancel each other, so the final expression between these two things are not that complicated. That's the reason we're trying to do simplification in general. The harder one, the original one, comes from some geometric equations you set up. This one is something you say, hey, even though I don't realize at the first, but I know a lot of trig identities. So I know something I wrote in the middle is actually redundant. So using the trig identity, I can simplify them. So this is not just for fun. Okay? Now we move on to the next one, which is an upgrade of what we just did. That is prove trig identities. And you say, we already know trig identities. Then you already know some simple trig identities. But in general, we have a lot of complicated trig identities, and you do not want to memorize them. Instead, you just want to prove they're true, and once you prove they're true, you can use them. But so instead of giving you a table for all possible trig identities, and automatically you know this is not going to work because there are infinite many. Okay. So instead, what to give you are the basics. And you can use it to derive or prove other complicated trig identities, which is a much more efficient way, or actually this is the only possible way for you to do it, because again, from the beginning, you cannot have a table for all possible ones. There are so many. Okay, after that, maybe you use this one to use in real life. Which originally come from some construction problem, or maybe some other problems. So from here you can see, as for this class is concerned, we only focus on how to prove that identity. But in real life, actually, you have to do one additional step. That is, once you get the identity, you use it to direct some kind of construction. All right. And there's nothing better than going over some examples. We will go over a lot of examples, just to let you see, okay, what the process is like. As I go over more examples in this, I'm pretty good with this, so I'm just going to go straightforwardly. For you, I would suggest, after the first several ones, pause the video every time I have a new problem, do it yourself, okay? And then only look at my answers when you finish what you have or when you get stuck. The first one is this. I have a trig identity. That is, the left equals to the right. And by the way, it's possible that it's not a trig identity. I just write them down and say, hey, is my computation correct? Now, how do we write this problem? It's like the following. The first thing you do is you draw. You don't have to, but this is what I use to clear my mind. So you clearly divide the left-hand side and the right-hand side. Okay? Then what you will do is you will keep simplifying the right-hand side. You will keep simplifying the left-hand side, pretending they're not the same. They have no relationships. Until one day you find, well, what I got here is exactly the same as what I got here. Then they match. Once they match, everything before match. So that's the process. Okay, your goal is simplify the left-hand side, simplify the right-hand side, and hopefully they become identical. They are not at first, of course. Okay, and which way to go? For simplification, we always go from the side which has more terms, because we're hoping they become fewer terms. So right-hand side equals. Then it's reduced to simplification, right? Tangent plus cotangent. I'm not a big fan of... Oh, I should use theta. Times. Okay, which equals times okay. Now simplification. This is 1, great, and you can see sine and sine cancel each other. When you simplify, suddenly you realize this equals the left-hand side already. Therefore, the identity is proved. Okay, so you work on one side, you work on the other side if necessary, until they look the same. That's what we have. Your goal is try to make sure the right-hand side equals to the left-hand side. And through the process, you're using trig identities and algebra. Therefore, even though this one, the last one, looks different from the first one, but you can guarantee it's still the same thing. That's why you can keep changing the format. Okay, let's try another one. We have the left, we have the right. So now, okay, I'm really not good at cosecant and cotangent, so maybe it's just me. I can change it to be sine, cosine. Which is pretty nice. They have the same denominator. So we are here. We can go more, go further, but the problem here is like we don't know which way we want to go further. But then you realize, wait a second, I need to get some hint from the left also. So one over a big fraction on the bottom And 1 over a big fraction is the same as flipping the fraction. So my goal is try to make sure this equals that. Now, what shall we do? Well, if you think about it, you have 2 fractions, right? To have a fraction, the only chance you have is the top equals the top and the bottom equals to the bottom. That's your only chance. Therefore, we better set the common denominator for these two. So at least the bottom are the same, and then our hope is the top are also going to be the same. So what's the common denominator? The common denominator is going to be this. And at least after you do that, the bottom will be the same. Our hope is, cross our finger, the top are going to be the same. So what's on the top if you want to do this? That's just sin x times another sin x. What do you want on here? That means your top should times the same thing, which is 1 minus cosine. From algebra, a plus b, a minus b is a squared minus b squared. The bottom are the same. Okay, are the top the same? Or equivalently, is sine squared the same as 1 minus cosine squared? The answer is yes by trig identity. So the identity is proved. So from here we can see sometimes maybe the right hand side you simplify, you got the left, or maybe you simplify the left, you got the right. But in most of the case, actually you need to simplify both until they finally give you some hint, so you can do some additional work to make them look similar. When can you stop? You can stop when you have some trivial trig identities, like what we have here, that is sine squared equals 1 minus cosine squared. There's really no more point to do more, because we know that is true. Okay, like I said, more examples, but pause anytime to try it by yourself. If we're in a real classroom, I will actually pause this and let you do it first before I review the answer. I think there's no point for me to do it for an online setting because you can pause by yourself. But don't just read what I have here, okay? You need to do it by yourself. Cosecant minus secant. Okay, classic, left-hand side. Cotangent, tangent, there's no identities. Sine, cosine, there's no identities. So probably my best chance is change u to be sine. Cosine over sine for cotangent. Sine over cosine. Okay, I know it's long. Be patient. Cosine squared theta minus sine squared theta. Sine theta, cosine theta, divided by sine theta plus cosine theta. By the way, you can start working on this also. My personal preference is actually work everything on one side to the end until you cannot simplify further. That's when you need some additional hint from the right hand side. Okay? If you go both way, maybe you missed and you do too much because maybe half the way they're already the same as each other. You just didn't recognize. So let's make sure the left is as simple as possible first. Or you can start from the right and make sure it's as simple as possible first from the beginning. All right. Can we do more? Well, at least dividing by something is the same as timing the reciprocal. I really do not like so many fractions on top of a fraction. So at least one thing I can do is I can make this times that. The rest will rely on your algebraic skills. Do you recognize the top can be factored out like this? Again, the classic a squared minus b squared identity. And the reason we want to do that is because once you do that, you find a common factor. And then what you have here is going to be nothing but cosine theta minus sine theta left. Sine theta, cosine theta on the bottom. Up to now, I think I'm good. I can simplify further, but I really don't know if it's going to help. This is simple enough. What about the right-hand side? By the looking of it, well, on the left it's sine cosine. We better change the same thing on the right. Now, we realize, well, fractions. And what do you realize? You realize they are the same already. That feels good, isn't it? It's so complicated from the beginning. There's no way you can see the connections, but now they are actually the same thing. Maybe this already give you some constructions of some kind of, the rooftop of a building. Okay? So, great. The identity is proved. We have done 3 examples so far. Again, I want to address several things. The first one is memorize the identities. Okay. Number 2 is your goal is to let the left-hand side to be the same as the right-hand side. Therefore, you can keep simplifying the left and the right separately. The final goal is make sure these are identical. Okay. The rest is just a test of how good you are with all the algebraic skills you have. All right. We can have more. In class, usually we do some additional exercise by yourself. But for online, I think that's good enough for me to stop here now. Because going more is kind of more redundant. And you can see more in your homework, so you can bring it to the discussion session. And then we can do more there, so you can see something live and ask questions. So I will just give you one more example. Remember, we have the identities of odd, even, and we haven't used it yet. So let's try one with these identities. Again, the key is you need to know the identities really well. Otherwise, you cannot reflect and recognize what's going on. This is very easy. So probably we want to start with the harder one and try to simplify. Pause, think about the identity. You either memorize it by algebraic expression or you remember it's odd for sine, it's odd for cosecant. So put a negative on everything. Algebra. Up to here, you probably want to do the same thing for the sine t. On the top, you have 1 minus sine squared t. On the bottom, you have dividing by this, which is the same as this. Okay. Now what do you have? Trig identity. You can go further. Maybe necessary, maybe not necessary, but now look at the right-hand side. Do you recognize Cosine over sine, that's cotangent. You square it, you square it. So this and this are the same. The identity is proved. That's all we need. Okay, so even though you have some negative t there, don't worry. Remember, memorize all the trig identities. So when you see something like that, it's very easy for you to reflect. And after that, the negative sign is nothing but algebra. You can easily do it. Okay, finally, we can have something. We can have something that look like this. And tangent x minus sine square x equals tangent x squared cosine squared x. Prove the identity. Well, how do you do that? So many things, right? So on the left, what do you have? You have tangent square minus sine square. You probably have nothing better other than change this to be sine square. Left hand side. Therefore, you probably want to do the same thing to get the common denominator. Fine. Oh, hold on. Keep going. 1 minus cosine. What do you know? It's gonna be sine square x times sine square x times cosine square x. All right. You can simplify further, like I said, but you also have the right hand side, so why don't you just start from here? Sine cosine, therefore I'm going to do sine cosine, which gives me cosine square, so great, the bottom match. And now check your work. They match. They match. For these two to match, there's no choice. Sine x has to be the same as the cosine x, square x. Do they match? They don't. And they will never match. Before, it's not clear they match or not, but once we have something look like this, you have the two parts. Every other parts are the same except for this part, and this part will never be the same. So what's your conclusion? It has to be this. And if the left-hand side does not equal to the right-hand side, what do you say? It is not an identity. Yes, I understand. You desperately want me to prove this, to show that the left-hand side equals to the right-hand side so you can do the construction. But through some mathematical argument, I tell you, this is not an identity, so go back and check your work. You definitely did something wrong there. It's not probably, you definitely did something wrong there. Otherwise, I can prove it. Okay, so this is actually a very, very efficient way to check, did you do the right thing in your measurement, in your constructions? Okay, that's all we have for this section. So basically, proving identities, simplify expressions. The key is, number 1, memorize and recognize the identities. The simple ones. We have 4 sets of them. Number 2 is doing algebra, and maybe you want to do a little bit of work on, formalizing your writings in the same way I write, because that's probably the most clear way that everybody will recognize what you're doing. Finally, if you did the left-hand side right and then the right-hand side, and somehow you are sure they're not the same. Sometimes they don't look the same simply because you didn't simplify further. But once you simplify to something really identical except for a small part, and you know that part is never identical, it's not because you didn't simplify further. That's the moment you start to say, hey, it is not an identity, because it goes against some identities that I know. Okay, so that's possible. When that happens, just simply write down this. And that will be enough for the problem. That's all for today. Oh, by the way, practice, practice, practice. If you feel confused and if you not making progress, practice. Same thing as the first time you learn algebra. A lot of practice will help you.